Hello, my name is Devin Protzko, and I'm a research assistant under the advisement of Dr. Guimond, supported by JCET, or Joint Center for Systems Technology, in accordance with UMBC and NASA. I want to thank AMS and the session supervisors for allowing the opportunity for me to present this work today. This current project falls under the branch of remote sensing and numerical modeling behind understanding the turbulence in hurricanes. The title of this work is Connecting Turbulent Eddies in Mature Hurricanes Through Wavelet Analysis on SAR and IWRAP Data. So let's get started. So to meet up with this 10-minute presentation cutoff, I'll try to breeze through some of these topics, but the presentation will follow something like this. Background for macroscopic motivation of the work, data sources, mainly comprising SAR, which is synthetic aperture radar, and IWRAP, or Imaging Wind and Rain Airborne Profiler. The methodology, that's where I'll explain what we do with the data, how we extract and filter what we want, results, conclusions, and finally, if we have time, some past work and potential future work with an LES or large eddy simulation relevant to this work. So for a general motivation, hurricanes are some of the most destructive natural disasters on Earth. So predicting both their trajectory and intensity is valuable. The intensity part is what is important here. So more to that, the accuracy of these predictions may be supported by furthering our understanding of relatively small-scale features in the storm, such as turbulent eddies on the scale of 1 to 3 kilometers. It has been shown through numerical modeling, such as by Gao and Guinness, that turbulence can increase the intensification rate of these mature hurricanes by up to 15%. So characterizing this turbulent regime on this scale may lead to a better understanding of the larger scale intensity cycles of mature hurricanes. Unfortunately, there is not an abundance of fine scale resolution data with Doppler capability available for large swaths of the storm. But fortunately, IWRAP offers fine-scale Doppler data capable of resolving real wind speed retrievals, while SAR offers large swaths of fine-scale backscatter intensity data. So linking these two data sets can be key to validating SAR's value and characterizing turbulent eddies. So this leads to the prediction value of the trajectory versus intensification, which leads to this, my handy-dandy NOAA app. I screenshotted these this past hurricane season on my NOAA app of a forecasted versus observed data here. So, for example, here, the hurricanes Eta and Iota were intense storms that hit Central America earlier this past season. They intensified from 1 to 4 and 5 in about 12 hours. So these examples further validate the idea that the accuracy of trajectory models have surpassed that of intensity models. In the left, you can see it was expected to be a 3 at landfall, but it actually was a 4 and earlier intensified to 5 by landfall. So some improvements can be made there in the intensity models. So as for background, here you can see the overall structure of the hurricane, where the bulk of the energy lies in the highly turbulent HBL, or hurricane boundary layer. The peak winds in a hurricane are at this lower level due to the warm core nature of the system, which interacts strongly with the ocean surface, producing significant vertical wind shear. On the right, you can see the schematic of the kinetic energy density as a function of wavelength for the physical processes controlling the intensification of the hurricanes. The black lines highlight the expected energy scaling from Kolmogorov turbulence theory, and red arrows denote the direction of nonlinear energy transfer. Our work is focused on this turbulent regime here. So as for past research work, we've done various work in turbulence, but we're starting to all connect it now with SAR. So done some past large eddy simulations with Dr. Guimond, and linking it through SAR would be pretty exciting, but that's for a future to tell. So our data sources of the work here is just the observational remote sensing data, the SAR and the IWRAP, not the LES. So our first observational data is SAR. It's the synthetic aperture radar. The horizontal winds in a hurricane put significant stress on the ocean surface. The high vertical wind shear in the HBL, hurricane boundary layer, produces turbulent eddies which leave an imprint on the ocean surface that the SAR can detect. The SAR is one of the highest resolution of earth science data available that we're aware of, as it provides a very large domain at a very fine resolution relatively of about 100 meters spatial. But where the Doppler provides phase shift data that provides velocity, SAR can provide magnitude of backscatter power. So to reiterate, since SAR contains data reflected by small-scale waves generated by the wind, the backscatter of these waves are related to the wind. This motivates the cross-referencing of the IWRAP real wind data with the SAR data-dense, very large-scale backscatter data. So the second observational data set is IWRAP, Imaging Wind and Rain Airborne Profiler. The figure on the left shows the measurement geometry of the conically scanning IWRAP and nadir viewing SFMR instruments on the NOAA P3. We aren't going to, in this talk, so much focus on the SFMR. We're only going to focus on the IWRAP data. But it retrieves a curtain file, and it's very high resolution with wind and reflectivity data, about 150 meter long track and 30 meter range sampling. And the biggest idea here is it's Doppler capable, so we get wind speed, but it's a smaller space and time coverage. But they fly through the inner core of the storm and gets very data dense retrievals. The retrievals are collected in these radial legs here that are about 30 to 45 kilometers long, and it retrieves these vertical curtain files of data. It measures backscatter, but we focus on the Doppler to wind speed data through an inversion algorithm, not reflectivity to wind speed. So it's not really important, but the KU band is higher frequency, so the signal is attenuated more in the eye wall, but C band comes into play, has a lower frequency advantage, so you get a fuller picture with the KU band and the C band, but we'll skip that. So the methodology here on the left, you can see the raw SAR backscatter data of Hurricane Dorian on the 29th of August in 2019. On the right is what's being processed. So now the question is, since SAR and IWRAP don't match up exactly with space and time, how do you build a database for statistical comparison? We're trying to create this sample that is as equivalent as possible for SAR and IWRAP. So we're trying to make it coincident with data, or make the data coincident with radius, resolution through interpolation, and track length. So we iterate with each degree in polar sections of SAR in the inner core of the storm. So it's a very large domain of data. We can kind of pick and choose what we want. So we make it coincident spatiotemporally with IWRAP as close as possible, and then draw statistical comparisons from there. And here's another example, another day of Hurricane Dorian. It's the 4th of September in 2019. And same way of preparing the SAR data as before, create an equivalent sample as coincident with radius, resolution, and track length, and then iterate by degree in polar sections of SAR. We downsample the IWRAP data, so it's in 2D curtain file, and we process it in one-dimensional. So we do an averaging technique after filtering. The filtering here is 1 to 5. The data is fully resolved at 1 kilometers, and it's convective above 5. So we filter it through this 1 to 5 kilometer filter before we run it through our wavelet analysis. So onto the wavelet analysis itself. Because of time limitations, I won't go into the details of wavelet analysis, but effectively, while Fourier transforms extract temporal scales of a signal, wavelet analysis provides the frequencies that exist in the signal, as well as where the frequencies exist in the signal. So this way, we can track what turbulent eddies exist in the storm, as well as where the turbulent eddies exist throughout the storm. Here's an example wavelet. So you have where it is and what it is. So we do this with our SAR data as a whole, and we get our retrievals. I'll just skip over to the results here. We do it with the IWRAP as well, and we have multiple data sets, including Hurricane Dorian, Rita, Ike, and Isabel. We have our results here that are somewhat Gaussian, of a peak at around 2 kilometers. So the turbulent eddies exist from 1 to 3 kilometers here, with most of those turbulent eddies being at a wavelength of around 2 kilometers. So the conclusion here, we're tight on time. So conclusion is the confirmed existence of the coherent turbulent eddies in the observational SAR and IWRAP data. We've identified these physical features. So we have a set correlation of SAR and IWRAP data. So we've linked these observational data sets, and now we can focus more on how they can impact the mean storm upscaling. And this was done with Dr. Guimond in 2018. So first off, we plan to submit this work to Remote Sensing Journal for publication. Once we identify similar statistical properties of the turbulent eddies, we can use the relatively large SAR domain to make more specific estimates of the impact of the eddies on the mean flow. So for example, the small-scale striations in the SAR data extend over large azimuthal distances and have repeating pattern and radius. So as stated earlier in a couple slides ago, through momentum budget analysis, it could be concluded that these eddies play an integral role in the intensity change of the hurricane. And as for the LES wavelet analysis, what energy is the energy moving? Is it upscale or downscale in vertically coherent structures? How are these structures related to the radial location of maximum shear? The results of this study can help motivate idealized numerical simulations of the vortex response to turbulent momentum, moisture, and heat fluxes in the boundary layer and air-sea interface. So I'm a bit over time, but as an extension here, the LES, Large Eddy Simulation Modeling extension, I can dive into very quickly. In 2018, we had some work regarding the coarse versus fine scale LES resolutions. It's kind of an argument of what resolutions are needed to resolve these turbulent eddies of 1 to 3 kilometer wavelength, and it was found that the 60 meter full resolution LES simulation was sufficient in resolving these wavelengths, whereas the coarse was not as effective. And here's the wavelet result. Here is the high grad LES model that solves the compressible non-hydrostatic Navier-Stokes equations with a finite volume and semi-implicit dynamic core. It's used to simulate these parameters were used to simulate the hurricane intensification process. Some details won't go into, but basically that's some fun work that could relate very effectively to the SAR and IWRAP work. I'd like to thank JCET, specifically Dr. DeMaz, and the UMBC STAR program for funding this work, Chris Jackson at NOAA for the SAR images, and finally we'd like to thank the data collection efforts and the teams that went into the IWRAP project. And here are references, and thank you so much for listening, and you can reach out to me. Best way would be through my email, devipro1@umbc.edu, devipro1@umbc.edu. Thank you so much.